Okay, so last week we finished the general idea of RG for sums of random variables, and if I want to summarize it, RG for sums of random variables. And if I want to summarize it, I would say that when you look on Sn, which is a summation I goes from 1 to n over xi minus n mu divided by some square of n to some power gamma, we basically managed to obtain scaling laws. So by performing the summation, doing this renormalization for each step, we eventually found what are the general scaling laws, or how to obtain general scaling laws for the cases when x's are correlated, uncorrelated. You've seen this specific situations where when xi average is finite, and also you've seen situation where xi average is actually diverging. Everything eventually can be obtained, all those summands can be obtained by using the RG steps. What we haven't covered, and it's very interesting, is how all of this is translated into dynamics, right? Because we summing up over many random variables, but in a lot of cases those random variables can be described as motion, right? So if I'm thinking of a specific particle that performing jumps, and those xi's are the distribution of the jumps of the particle, out of this Sn, right, I can obtain the different positions of the particles, because summation of I goes from 1 to n over xi will be this n to the power of gamma multiplied by Sn plus mu of n. And if we know that at large n, this guy eventually becomes independent of n, okay, so for large n, S of n converges to a random variable, we obtain that the summation I goes from 1 to n over xi is n to the power gamma, this p plus mu of n. So what we see is that the position of the particle, which is the sum of all the many different displacements, is actually the random variable p that we somehow can compute by using this RG RG treatment. Here we have those exponent gamma, and n is the number of steps. So we can create many different dynamics, which is going to be based on how the xi's are correlated. Is the correlation is short range, long range? How the different xi's, do they actually have a finite mean? They have a finite variance? What are the correlations, etc., 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 etc. So all of this somehow can be created and translated into dynamical systems that we won't cover. Now, this simple equation afterwards can be translated also in continuum matter. So when the different delta xi's are infinitesimal, and we can create something which is called the Langevin equation and Fokker-Planck equation. But this is not part of this class. But from RG, we can create dynamics for any kind of system or any kind of particles, independently if there are correlations, no correlations. The only thing that is affected is the specific coefficients over here. We also haven't covered something which is very novel for sums of random variables, and this is the extreme events. What I mean by extreme events, or let's say rare events, So for example, we do know the following thing. We know that if we take a sum, I goes from 1 to n over xi, minus n of mu divided by its square root of n, this guy converges to a Gaussian representation, random variable, when n is large. Right? But we can also do something different, and this difference will be what happens to the sum. What happens to the sum, not as a function of n. So what we have done usually, we looked on this Sn, and we have taken n to be extremely large. Okay, but if we'll do something else, we'll take this Sn, okay, and we say, well, this Sn for fixed n, what is the distribution? So what is the distribution of Sn of S? Okay. So instead of taking n to be extremely large and using those RG ideas that gives us all those scaling laws that we've seen, what it gives us the random variable, which is basically the Gaussian in the center. Okay, but we can do something else. We can fix n and ask what are the distribution of the extreme events, of the rare events of this random variable. And also there, this RG algorithm can be applicable, and there is a different fixed point that creates a very different than Gaussian decay towards the zero. So the universality class that I told you about, it's the more classical one, and it's applicable to the center. And in the center, for example, for the case of uncorrelated random variables, you will get the central limit theorem, which is the Gaussian. But around 5-6 years ago, the different approach was taken, is to look on this random variable, fix n, look on what the distribution of this random variable, how it looks like when this Sn extremely large, positive or negative, and then apply this RG algorithm. And what we obtained that there is a different scaling law, there's absolutely different behavior for the tails. And actually it's here, it decays as e to the power minus s. So different scaling, different critical exponents, everything is completely different just for the tails. Why? Because, and it was the question that was asked previously last week, so Stas, you can find a fixed point. Oh, you found a fixed point, and you can then explore this fixed point, you do this cumulative expansion, etc., etc. So all these technicalities that we've done. It sounds a little difficult, but it's not that difficult, you've seen it. But who tells you that that's the only fixed point? And the answer, you don't know. Because you have a big phase space, and in this big phase space, well, if you found a specific fixed point, it doesn't tell you that there are no other fixed points in the phase space. You have to search through it. And the RG just tells you usually what happens around the fixed point. It doesn't tell you that there are other or no other fixed points. You have to solve a specific equation. So this is very recent that there is an additional fixed point, but not for the center and not as a function of large n, but actually for the large values of this guy. But extremely novel material. We're talking about the last 3 years. How it's connected to what we started this class with. Remember, once upon a time, we looked on the Ginzburg-Landau theory. Ginzburg-Landau for fields. Right. So how this RG ideas that I developed to the sums of random variables, how it's applicable to all those ideas of fields. So what we have done, we build a field theory starting from some lattice, Afterwards, we build the partition function. We describe this partition function by using a Hamiltonian. We had a functional integration. And then we found a specific solution. We used the mean field approximation in order to obtain what is the partition function. Right? And at some point, we got stuck with this mean field because we proved that for D between 4 and between 1, the dimensionality between 1 and 4, okay, the mean field solution is not applicable. And I promised to you that somehow, or some rescue, can be found by using these ideas of RG. So that's what we are going to do today, try and establish some sort of connection between these ideas of RGs that I developed for the random variables and what happens to the Ginzburg-Landau theory of fields. Historically, it was done absolutely the other way around. So RG was developed during the 70s by Kadanoff and Wilson. Wilson got a Nobel Prize for this eventually. And it was developed for Ising models and Ginzburg-Landau theory of fields. And only very recently it was understood that it can be applied to sums of random variables. And it's actually much more easier and applicable to those cases of random variables and not to fields. And I will try and describe to you why and how. All right, so we're going back to the Ginzburg-Landau theory for fields, and let's try to understand how those ideas of scaling and invariant probability density functions, how it's applicable to something which fields, right? So what do we have? The basic quantity that we wanted to compute, which was the partition function, it's an integral, a functional integral, over all the possible representations of the fields that we have, phi, okay? And we had an exponent of the h of phi. Okay. Now, what it basically means, this integration. So we have some sort of the Hamiltonian. So let's assume that our Hamiltonian h of phi takes the simplest case of 1/2 or gradient of phi, let's put a kappa over here, plus r divided by 2 phi squared. So even if you're not going to the phi4 theory, this is the Gaussian simplest theory that you can look on. This integration basically tells you, so for example, if you're operating in 1D, and this is your x, okay, and if you have a system which is limited between 0 and L, this functional integration tells you, well, you have to consider any possible function phi. So you take phi that looks like this, okay? You plug it into the your Hamiltonian, and you produce one single contribution to this integral. Now, afterwards, you take another phi, which looks like this, for example. This produces another contribution to this integral. And eventually you have to go over all possible phis that you can imagine. Okay. So this is phi, and those are different functions that you have to consider. The mean field approach, by the way, was, let's take one specific phi, one single phi, such that h of phi is going to be minimal, okay? And you're taking one single representation. So, for example, something like this, let's call it f min, okay? So this is your phi of mean. How the computation of this guy is actually related to random variables and etc. 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 And the answer is, this is the Boltzmann factor, right? So the moment that I've taken phi, let's take phi star, for example, the probability to observe the specific representation, okay, is going to be probability of phi star is going to be 1 over z e to the power minus h of phi. Right. So if you know this z, your partition function, the Boltzmann theory tells you, well, if you have a system, okay, and phi describes your magnetization, okay, phi a function of x, then the probability to observe specifically this magnetization as a function of x, okay, is going to be this function over here. So you have a Hamiltonian, you plug inside your specific phi star, and this is your probability. Okay. So the computation of z, eventually, the computation of z is related to computations of different probabilities of different phi stars. Okay. So this is the first analogy between the field representation and the phi star representation, or the random variables representation. We treat different representations, okay, not a specific value of random variable, but different realizations of the field as a random variable. Okay. This is what we are doing in the Ginzburg-Landau theory. Okay. So if, for example, in the summation of random variables, we take only specific values of those random variables, here you take different realizations for different x's. Okay? So you can say that random variables, and all the RG that we have done so far, is to apply to a quantity which is zero-dimensional. Okay? There is no dimension to the random variable. It is a specific values, okay, that are distributed somehow. Fields, it's not a specific value for this point. It's also specific values for many different points. Right? So you can say that random variable is as taking a specific cut, right, at a specific x, and look on the different values the function phi can obtain at this specific x0. Okay. Now, here phi is going to have different realizations, different values. So phi at x0 is a zero-dimensional random variable. So what we have done so far is to compute realizations of zero-dimensional random variables. Okay. Instead, for Ginzburg-Landau theory, you're not looking on zero-dimensional quantities. You're looking on one-dimensional, two-dimensional, three-dimensional, four-dimensional quantities, because it's not that phi have random values at specific x0. It has random variables for many different x's. Okay.
But it's the random variables are different. It's not random like what you said about the random variable.
When I'm looking on this guy, is you're treating phi star as a random with a specific distribution. Okay? So you say, well, there is a physical reason. The physical reason is in your Hamiltonian. Okay? So the moment that you've written that there is a probability to observe a specific realization phi star, what is the probability? This guy. This means that phi star is a random variable, not zero-dimensional, but d-dimensional. That's it. Okay? Okay.
And for mean field, it will reveal the gradient, which will allow us to use the Gaussian, which we saw beforehand.
Okay. Not exactly. So, you see, there are different probabilities for different realizations. Okay? This is already encoded in this partition function. What is the mean field? In mean field, we say there is one single realization, one single phi. So P of phi equals a delta function of phi minus phi mu. That's it. Mean field is not saying I can have very different realizations. Mean field is saying I have a very specific realization. This is my solution. This is like a natural, but that's oversimplifying. Okay, I have only one solution, and this is the solution F main that came from minimization of the Hamiltonian, the solution of the mean field. So instead of having a distribution of different realizations, mean field tells us there is one single realization. Okay, therefore its the probability is a delta function. Why not delta function? Why delta function not one? Because it's a continuous vector. Okay, that's it. That's it. So this is oversimplification. So it's like if I had a summation of random variables from n, I would say, well, it's not a distribution. It's have a specific value. Let's say 7. Okay, 7 multiplied by n. It's not a distributed random variable. It's a regular variable. Okay. This is the solution of the mean field. Now, we don't want to do this, right? This led us to the specific problem that in dimensionality between 1 and 3, we proved that fluctuations are important and there is not a singular solution to the problem. Okay? This is what we proved for phi to the 4th, but it's actually dependent on your Hamiltonian. But there are always critical dimensions. Lower critical dimension and higher critical dimension. In between them, the mean field solution does not exist. Okay? Or it's simply wrong. So what we want to try and obtain is apply this RG method for random variables. Now we see that the realizations are also random variables, right? So we will apply this method of RG to random realizations, right? In hope that eventually there is going to be a scaling law. What I mean by scaling law, that after a while, okay, so I'm starting with specific distribution that I cannot really say what it is. But I apply RG 1 step and 2 steps and 3 steps and 4 steps. And eventually, for the case of random variables, I reached a fixed point. What was the fixed point? That there is a scaling law which was not dependent on additional applications of RG steps. Right? This was applicable to random variables. I want to do the same exact procedure for realizations of phi. I want to apply RG once and twice and 3 times, such that eventually I will reach a fixed point for the distributions. Okay. Now, this fixed point is not going to be a delta function. It's probably not going to be a delta function, okay, because RG is much richer than the mean field approximation. It's not choosing one specific. It will give me a specific realization, not specific realization, but specific distribution of realizations. And I can understand something from this distribution of realizations, right? The idea is, it is not a delta function because we proved that their fluctuations are super important. So the question is, what is the distribution, right? What is the distribution? So let's see, we'll use this analogy, RG, for random variables that I hope you already understand, RG for fields, RG for random variables, RG for fields. So the first step of renormalization group is to create a single step, right? So the creation of single step is to say, well, let's define SB, RG for random variables. Let's create a random variable, which is SB, which is a summation I goes from 1 to B of xi. I divided by B. Okay, and you remember I said, well, let's divide it by some b to the power gamma. But I want to write this a little bit differently. I want to write it as, let's divide it by b, which it's simple averaging, and multiply this guy by b to the power delta. Now, this part is critical, this multiplication by b to the delta. Because what he have shown, for example, that the COT appears when the steps are 1b xi divided by square root of b. Now the division by square root of b, it is a summation. I goes from 1 to b over xi. Division by b, I'm multiplying by b to the 1/2. If I won't divide by this b to the 1/2, I won't get the square root of b, and I won't get the scaling law. Now, more of that, if I'm looking only in whatever stands in my parentheses, or what stands in front of the multiplication by b to the 1/2, is just summation of random variables and division by b. So this is a simple average, right? This is a simple average. Now, I know by the law of large numbers that this guy, if I would take b to be infinity, this guy goes to a constant number. So if the average of all the xi is 0, this guy go by probability, okay? Not on average, but by probability, this will go to 0. Okay? The magic happens if I multiply it by b to the power delta, okay? And then take the limit of b to be very, very large, so basically dividing it by square root of b, then by probability, that's not what occurs. Okay? So if I would just take the average, the average converges to a constant number. But if I'm not taking the average, but I'm multiplying it by b to the delta, all of this converges to a random number, which is, for large b, independent of b. That's what we've shown. Now, I want to do exactly the same thing for fields. So RG for fields. RG for fields. Now, so first of all, what's the idea? I take many different xi's. Remember, this is like choosing a field at specific point, and I average over different xi's. All right. So my field lives, for example, in a box. So I choose a specific point, call it x, okay? And my field is, well, the realization, my field can have many different realizations, right? So this is realization of the magnetization that I have inside. Now, I'm taking a box around this x, all right? And I'm saying I will average of the different properties of my field inside this box, and I will call it one single value, right? One single value. So like here, instead of looking on many different random variables, I sum them, I average over many different random variables, and I multiply it by b to the delta. Here, I have many different points of values of the fees inside this box, right? Each value of my field inside the box is like a single random variable, and I have to average over all the possible different values that I have inside the box. Okay, so I'll take an integral of phi of x ddx inside this box around this point b of x. Right? Now, the size of this box is b by b. Okay? So here, I divided by the total number of random variables that I'm included in this averaging. How many different values of phi I have inside this box?
B
B squared. So I divide it by over b squared. And in d dimensions, it's not b squared, it's just b to the power d. Okay? So this is this step of averaging. Okay? This is the first step of averaging. Instead of using random variables, I'm using the field inside a specific box, and I average over it. Now, here, I multiplied it by b to the some power delta. I multiplied here b to some power delta. I don't know yet what this exponent delta is. I don't know yet what this exponent delta is. All right? So, this guy is my new field at position x. Okay. Right, so here I created a one single value. This is a single step in RG for random variables. Okay, this simple step. For fields, a single step is for different x's, performing an average of the field inside this box multiplied by some b to the power delta. What is delta? Still not, I don't know. Okay, right. Now, here comes a little difference between what happens in RG and what for random variables and what happens in fields. So, in fields, why it's different? Because I have many boxes, right? So I have this box, and I have another box, and I have another box, and another box, and another box, and another box, and another box. Okay? So I have many x's. Right? Now, this is something which is not present in the random variable perspective, is that when I'm looking and I basically, for each box, instead of having many different values of the field, I taking each box and gave it a exactly one value provided by this formula. Okay? So for different x's, I have different specific values. It's going to be black over here, and it's going to be red, and it's going to be green. Okay. Now, the additional step that we have to perform is, well, we created larger or fields with larger boxes. So instead of looking on this as a function of larger boxes, we can say, let's make everything scale by b. Okay? So this is size of b by b, this is size of b by b, this is size of b by b, and this is the size of b by b. But eventually I want everything, okay, like zooming out. So I will have a black spot over here, and over here, and over here. And I will have a green dots which sit over, that's right. So it sits over here, and over here, and over here. And I will have green dots that sit over here, and over here, over here, over here, over here, over here. So I zoom out, and I look on this big perspective as if I have single values of this field. Here it's black, 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 green, 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 green. But I zoomed out. So the perspective have also to be modified. Okay. So basically, I'm changing the scale of my coordinates. This is for x. And then I will have x prime, which is simply x divided by b. That's it. Okay? So you average, which is coarse graining, instead of having, I have different values inside this box. I have one single value, but afterwards you also have to change your perspective. We'll see exactly why. So this additional step is crucial. Your perspective has to be changed. It's like you're looking on a system, you coarse grain, you zoomed out, and then you're looking on your system again. Okay, so this is a single RG step. Now, how we operated the moment that we created a single RG step for random variables. What we have done, we looked on f of k, which is e to the power I k s k sb average. We looked on the characteristic function. The characteristic function describes the probability density function in Fourier space of this new random variable sb. Okay, and the idea of RG is that you apply your RG step on fb of k, and eventually you get fb of k. Right? So you're getting a self-similarity for the characteristic function. So you find a quantity that describes the probability density function of this SB, and you claim the following: I apply a single RG step, and this single RG step is not modifying the probability density function. The distribution of this guy stays exactly the same. And we operated in this Fourier space trying to see when there is a fixed point for the characteristic function. Okay. Now, what is the analog of the characteristic function for the fields? Okay, so we do not go exactly to the characteristic function, but we're saying, all right, so what describes the probability density function of the field? So we know that P of phi is 1 over z e to the power minus h of phi. Now we perform some sort of transformation. What is the transformation that we perform? We perform transformation from phi to large phi. Okay. And the idea is that eventually, after we do this transformation, this is RG step. After we complete this RG step, we know that P of phi should somehow transform to probability of phi. Now, but this probability of phi is going to be what? Is going to be proportional to e to the power minus some h effective of phi. So here, the RG step, you operate on the characteristic function and you get exactly the same characteristic function. In Ginzburg-Landau field theory, this idea is you had a Hamiltonian of phi. You apply an RG step. Okay. The fixed point arrives when you get exactly the same Hamiltonian. It's called star. Okay? This is an RG step. Because what you do, basically, you modify the probability density function. You start with one single variable, okay, and then you have 2 single variables and 3 single variables. You accumulate single variables. The probability density function is modified from the distribution of a single variable to a distribution of a sum of these 2 single variables. So it's a convolution, right? The moment you have done this modification, you have a convolution of 2 probability density functions. Okay, this is the simple RG step. Okay, now here you do something very, very different. You started with one single variable, which is your fields. You summed up over different fields and divided by BD, exactly as you've done over here. All right. Now, this means that you performed a convolution of many, many, many fields. It's called the marginalization. You marginalized over different fields and squished them into a specific one point. Now, what happened? If previously you had this probability density function, you performed a convolution, you have another probability density function. You can always say this new probability density function, I will describe as e to the power minus e h effective. Right? I will write it down as follows. If you don't like this hand waving, I will write it exactly. So, for random variables, p of s b of s is the integration of dx1, dx2, dxb of probability, the probability of x1, x2, xb. And here I have a delta function of sb minus a summation of I goes from 1 to b xi divided by b multiplied by b to the power delta. This is the transformation that I performed. Okay? It's a convolution. Now, if I do this for large phi, this is exactly the same. I just have to perform a functional integration. So here it's a regular integration of the different values of the different x1, x2, x3 up to xb. Here I have to perform over all possible values inside this box of the field phi, and I have a probability of this field phi, and I should get that all those different fields phi go to this large phi description by using a delta function. So it's multiplication of all possible x in my box. Okay, and here I have delta of phi of x minus this step over here, large phi of x minus 1 over b of d and integration b of x, phi of x, d dx, and b to the power delta. Essentially, I've done a convolution for the random variables. I'm also doing a convolution for the fields. Now, the moment that I do the convolution for the fields, I can always write this down. As p of phi is sum 1 over z tilde e to the power minus h effective of phi. That's it. So the RG step is transformation of one Hamiltonian into another Hamiltonian. Okay, and the fixed point arrives when RG does not do anything at all. No. So the idea of RG is to find these fixed points and operate on the fixed point itself. And the claim is, as for random variables, I found a fixed point. For example, the Gaussian fixed point. You've seen a Levy fixed point. You've seen what happens when I have correlations, etc., etc., etc. The same I should do. Okay, so the same I should do also for fields. right? Because the structure is exactly the same. You average, you multiply, and that's it. Here, you average, you multiply, and that's it. Transformation. Instead of the characteristic function, you look on the Hamiltonians. Characteristic function defines the probability density function. Hamiltonian defines the probability density function. Same story. But how exactly you do this, right? So it's very nice, a lot of functional integrations. How you do this, right? So let's see how these RG and also how eventually you perform this rescaling, right? Because this is something that it's not present in the random variables. I want to zoom out, and change my perspective when I'm looking on the system. How I do this. So what we will try to do now, is to look on a simple example of a Gaussian. Now, why a Gaussian? If you remember, the example that we started, the RG exploration for the random variables, was Gaussian. And the Gaussian central limit theorem is probably the most basic and also the most wide fixed point that we know for random variables. But it's also the same story for fields. Gaussian, Hamiltonian, is a fixed point. So we always ask ourselves why Gaussians are so apparent in nature. Right? So this is due to the central limit theorem. You can also ask yourself why Gaussians in so many physical theories. Okay? There are different theories from hydrodynamics to statistical physics to quantum mechanics, high energy particles. The Gaussians are always everywhere. And the answer is because it's a fixed point. Fixed point not only for the random variables, it's fixed point for many other interactions as well. Okay, it's hard to say where the Gaussian fixed point starts and when some other fixed point begins or ends, but Gaussian is centrally a fixed point. It's a strong attractor, and we will start with the Gaussian fixed point. Now, don't be fooled. Gaussian fixed point is not a mean field solution. Okay? It's not a mean field solution. Mean field solution is just taking a specific realization, for example, saying phi equals to 0, okay, the magnetization is 0, and that's it. It's not a distribution, it's a delta function. Gaussian fixed point will tell us that the distribution of the different fields is Gaussian. Okay? So it's the difference between saying I have a sum of random variables and it's not distributed, it always has one single number as an outcome, or saying the sum of random variables is distributed according to Gaussian. The same happens over here. I have different fields. Eventually the Hamiltonian that describes this, when I apply RG, okay, I'm changing my perspective, will be Gaussian. Okay, so let's start. Do this perspective of eventually find or trying to look what happens to the Hamiltonians and how we apply these ideas of RG from random variables. Main point. For random variables, everything was done in Fourier space. It's more natural to work over there. We will see that the same happens for RG for fields. It's much more natural, much more easier to work in Fourier space. And let us see why. Okay, so first of all, let's define our RG step. So working at the Gaussian fixed point. So for random variables, you define what is your single RG step. The same is going to happen over here. Now I remind you that the first step was simply averaging. So this is phi at some point x. It is 1 over b, an integration at some box around the point large x of phi of x d dx, and we have to multiply everything by b to some delta. Okay. This is what we do. Okay. Now, I remind you that we want to eventually to transform everything to Fourier space. So I want to see what is this. This is a single RG step, right? We don't really know what this single RG step does on the level of Hamiltonians, okay? But we know the following. We know that it takes a different representation of the field inside a specific box. Okay, so there are many blue and some red and some green inside, right? And it smashes everything up, right? So you have something in between on my hand at least. Okay, so this is this operation. Now I want to understand what this operation does in the Fourier space. Okay, so I also exactly did it for in the Fourier, in the random variables. I looked on a single random variable at the Fourier space. So what we do, we say the following. So we take this phi of x, and we say that it's integration over k of phi of k ei kx dk. Right? So we use the Fourier representation of this guy. Now, and this is an interesting point. So the integration is not over all possible case. Why the integration is not for all possible case? Because remember, eventually, a fine structure of my lattice will come out. Okay, so k is 1 over the wavelength. So at some point, I will go below the scale of the lattice on which my field is built. So there is always a cutoff. Let's call it large lambda. Okay, and I don't go in my case above this lambda. Now, where this cutoff comes from, I know that the structure, my field, always started by a specific lattice. The representation of the field was built such that there is a lattice, and I have taken the continuum limit of this lattice in order to describe the field. So if you remember the Debye model, right? So there are particles sitting on a specific lattice, and at some point you cannot take the k vector such it describes the distances, interlattice distances. The same happens over here. Okay? Since the field, this original field, was taken by some sort of a continuous limit of this lattice, but this lattice interspace has a distance a, some specific minimal distance a, any information about the x's that are smaller than a's, the delta x's that are smaller than a's, is meaningless because nothing actually sits over here. Okay? There is no masses, no particle, nothing. This means that k has to be smaller than something that's this 1 over a. Okay? So I have a upper cutoff of lambda in my description. Okay. Now I take this guy and I plug it inside. b over delta 1 over b, an integration b of x, and here I have an integral of phi of k, eik x dk, and here the k is smaller, this upper limit, big lambda. I switch the order of the integrations, and here I have dx, ddx. Okay. I switch the order of the integration, b to the d, and I have, that is b delta. Here I have phi of k, integral of k smaller than large lambda, and here I have phi of k. Okay, and what I have inside, it is w, or write it down as an integral, 1 over b to the d, an integral around this x, large x point, eik x d dx. So I can write it down as b to the delta, an integral of k smaller than this limit, phi of k. Here I can say it's some sort of a filter, w, which depends on side b, and k. I integrated over all the x's, so it's going to be dependent on k only. So this is a specific integration of phi k w k. Now, what this means? This means that eventually I'm not, in order to describe my general new field, large phi, I'm having I can represent it as some sort of an integration of phi k w k. Okay, I can do that. Now, why I can do that? Well, there is, I showed you on the board, and this wb of k, I can say, well, it's some sort of a filter. Why it's some sort of filter? So let's see what happens, for example, in yd. What is wb is? It is a property of the averaging that sits over here. Notice that b to the power delta is just here, and everything that's related to averaging sits inside this wbk. Okay. So for d equals 1, what we know that wb of k, it's 1 over b, an integration of x minus b divided by half, large X, and x plus b divided by half. So this is the averaging over my specific box of size b. In the center of the box, I put my point, and I average of everything of size b half to the left and b half to the right, or b half to the left and b half to the right. So here what I have, eikx dx, which equals to, I can switch my integrals, x going to be u plus large x. Okay, so here it is 1 over b, an integration of b divided by 1/2 minus b divided by half, 1/2, because when x is equals to large x, those large x's are just cancel out. And here I have e to the power I, k, and here instead of x, I'm plotting u plus large x, dx, or du. So what we see, we can take out e to the power I, k, x, and here I have an integral, 1 over b minus b divided by 2, b divided by 2, e I k u du. Okay. Now, I perform this integration explicitly, so I have 1 over b e I k large x, okay? And here instead, I have e I k u divided by I k between b to the 1/2 and b to the 1/2. So what we see is WB of k equals to EIK x multiplied by async 2 sine of KB divided by 2 divided by KB. So what happened? I applied this in one dimension. I have this guy. I should have dk over here. And dk over here. I applied this in one dimension. And in one dimension, I got the following, that phi of x equals to b to the delta, an integral of k smaller than lambda, phi of k, which I know what they are, right? Those are the original representations of the fields. I have this guy, 2 sin kb divided by 2 divided by kb, okay, multiplied by e to the power I k large X dk. Now, this is the filter. Why? Because if you plot this guy, as a function of k, and this is a sinc kb divided by 2 divided by kb, it behaves like this. Okay. And this is this scale, 1 over b, 1 over b. So the averaging procedure in k-space, the averaging procedure, it tells us, all right, you look on fx b to the delta, it as if what you've done, you've killed all the k's that are larger than 1 over b. Right? That's it. So the averaging in real space, when you look on the modes, when you look in Fourier space, you're basically saying, I'm looking only on specific portion of the k-space. Okay. The averaging procedure is saying, oh, let's kill all the k's, all the k's larger than 1b are not contributing. Okay.
So it's like, since k is the inverse of x, when we do x zoom out, when we do it in k, we do zoom in. Right?
Exactly. This is exactly what happens. So you zoom out, you basically says, instead of having the knowledge of whatever happens inside, and you smurge everything into one single point, is just saying, oh, I don't care about large k's. I only care about small k's. Okay? This is exactly what it tells us. All right? So a single RG step is doing in k-space a cutoff, right? Doing a specific cutoff in k-space. That's it. Okay. Now you say, well, Stas, it's not exactly a cutoff because you have those wiggling parts, etc., etc., etc. But it is. It's almost as a cutoff. Now, moreover, so this is the original idea. Kenneth Wilson, who got a Nobel Prize for this, he said, so look on this. Look on this guy. I can say the following. So if I'm doing this in 1D, I can say, so basically, phi of x is an integral, right, of k smaller than delta of phi large of k e to the power I k x dk, right? So what we see is that phi large of k equals to phi of k, at least in 1D, right? Multiplied by 2 sin of kb divided by 2 divided by kb, right? So if you start from the averaging perspective, it is like taking the Fourier coefficients or Fourier modes of field of your new field and representing them by old modes multiplied by this filter. Now, this filter is ugly. It is a sink. So Wilsonian idea was even simpler. Wilson told us thought about the following. So instead of using the sin, k, kb, etc., this happens because you start from a real space averaging. But this is actually more important. This cutoff in k space. So Wilson said, I want to describe the averaging not for real space. I want to describe the averaging in k space. And what Wilson told us? Wilson told us that, I forgot something. There was b to the delta, right? So it's also b to the delta. So because it was over here. So Wilsonian. Wilson told us that it is phi of k is b to the delta, phi of k, and here he introduced w of k. And what is w of k? Or w tilde. We already have it. So what is w of k? Wilson wanted a clear cutoff. He doesn't want the sink, he doesn't for their Gaussians, doesn't want there anything. He wants a cutoff. Right? So when I'm doing building a box for averaging in real space, it creates a nasty functions in k space. So I would do exactly the same, introducing the cutoff in k space. It's as I'm doing the average in real space, but it's nicer in the Fourier space. Okay. So Wilson said the following. Do this, and w of k, and he wanted it to be connected, not just to some portion of b, but he said it is lambda divided by d, and your maximal size lambda divided by d, and it is 1 over here, and it's 0 everywhere else. Okay? So it's a pulse. It's not just saying, he said that the sink is a pulse. No, the perspective is different. So what I've described to you is the natural transformation from random variables to the averaging procedure for fields. But because you average in real space, it's nasty in Fourier space, this W, so no, I will do this in Fourier space and that's it. Okay. So, because it's actually nicer, otherwise we have to treat different ugly sinks and etc. This is what we do. So the averaging procedure, the single RG transformation for the fields in the Fourier space, it's like this. Okay? So you have a cutoff. You have a clear cutoff. All right. So now what we know that how this single RG step is operating in the K-space. Let's see what happens to the Hamiltonian, right? Because eventually it's not enough to say what happens to the random variable. It's important to say what happened to the characteristic function. For fields, it's not enough to say what happens to the modes of the field. It's important to say what happens to the Hamiltonian, because it should converge to a specific distribution. Okay, so remember, what is our Hamiltonian? The Hamiltonian was of phi of x, right? And it's 1/2 an integral of what d dx of the grad of phi squared plus r phi squared. That's it. So this is the simplest phi to the 2 Hamiltonian. Okay. Now, we have seen it already that if I can write it down in Fourier space as follows, I've seen it several times already. So h of phi of k, it's an integral 1/2 from all the possible k's smaller than lambda. Okay, and here we have I should have a kappa. I should have a kappa over here. No, but forget about the kappa. I don't care about the kappa. So this is k squared plus r phi of k squared dk. Okay. This is the Hamiltonian in k-space. Since we want to operate in k-space, we also want to see what happens to the Hamiltonian in k-space. Okay. This transition we've seen already twice or 3 times when we were talking about unitary lambda. Okay, next step. We want to represent this old Hamiltonian not in terms the phi of k, but in terms of large phi. Okay, now how difficult it can be. So you have to plug in place of every phi of k, this large phi of k, but you have a cutoff. So you take this integral and you split it into 2. So h of phi of k equals to 1/2 an integral k smaller than lambda divided by d of k squared plus r phi k absolute value squared dk plus 1/2 an integral over k larger than lambda divided by d and smaller than lambda. Okay, and here I have k squared plus r phi of k squared dk. So this is h for k smaller than lambda, and this is h for k larger than lambda. Now, this Hamiltonian is present in the z function, right? So in the z function, there is an integral of d of phi, okay? And here you have e to the minus h. Now we write this as an integral of d of phi write this as multiplication of all the k's which are larger than smaller than lambda divided by d of d phi of k of e to the power minus h smaller multiplied by the multiplication of all the k's which are smaller than lambda, larger than lambda divided by d, e to the power minus h larger, d phi of k. So you can separate it into multiplication of whatever the contribution of the Hamiltonian with smaller modes and the computation of the Hamiltonian with the higher modes. So basically, you're saying that you can integrate out all those modes. You perform this integration. All the modes are independent. Okay? All the modes are independent. So you say all of this z is transformed to a constant multiplied by only of the k smaller than lambda divided by d, d phi k, e to the power minus h smaller of phi of k. You don't care, you absolutely don't care about the k values that are for larger modes. Why? Because it's contributing, it's a Gaussian integration. Right? You have a Gaussian integral over here. It's a Gaussian integration, so it contributes a constant. Constant is just saying, as my Hamiltonian, is something plus a constant. You never care about additive constants when you deal with Hamiltonians, right? So the halfway through the procedure of a single RG step is to say, I perform this modification, I separate it into two Hamiltonians. The Hamiltonians with modes which are larger than specific threshold, I don't care about them. Okay? Why? Because I can make this contribution, integration, it contributes a constant number. I don't care about constant numbers. So we only look on the following Hamiltonian, which is h effective of phi of k. It is 1/2 an integral k smaller than lambda divided by d of k squared plus r multiplied by phi k absolute value squared dk. Okay. I erased it where it was over here, but I had a connection. The connection was phi of k is b to the delta multiplied by phi of k multiplied by this filter w of k. Now, we notice that w of k it is 0 if k larger than lambda divided by d and 1 otherwise. So instead of representing this Hamiltonian by using the original modes, we can plug inside, you notice we integrated out all the modes with k's that are larger than lambda divided by v. So we can say that H effective of the Hamiltonian now of large phi of k is 1/2 an integral k smaller than lambda divided by v of k squared plus r, and instead of phi of k we write b to the minus delta phi of k absolute value squared dk. This is our effective Hamiltonian. We integrated everything out. All the large k's are independent of phi k's. We integrate them out. This is what's left. Okay. So we're almost there. We're almost there. Now, the next thing is, well, the original Hamiltonian, I remind you, the original Hamiltonian was an integral over k, not up to lambda divided by b, but up to lambda. So I want to rescale everything backwards. I shrink everything, I replace the modes by the average modes, and I want to shrink everything backwards. Okay, this is the zoom out procedure. Okay, so I'm saying, let's look on k prime. What is k prime? K prime equals k multiplied by b. Okay. When I do this transformation, so what happens? H effective of phi of k, k prime, okay, equals to 1/2 an integral. So k was smaller than lambda divided by b. K prime is going to be smaller than lambda. So k smaller than lambda. What happens here? Instead of k squared, I have k prime divided by b squared plus r. Here I have b to the power minus 2 delta. Okay. Here I have phi absolute value squared, but not of k, but of k prime divided by b. Right? Because instead of k, I have k prime divided by b. And what I have over here. So when I'm saying this is dk, k is a vector. The dimensionality is d. So it is dk prime 1 over b to the power d. So the single RG step, when I transform all the modes, it's almost like the original one, but I have differences. What are the differences? So first of all, I have different multiplications. B to the minus 2 delta, b to the d. Here I have k prime divided by b squared. And what is most importantly, I have this phi k prime divided by b. So it's definitely not the original Hamiltonian. Okay? Definitely not the original Hamiltonian. So I want to replace this phi k prime divided by b by doing the following trick. So I'm saying the following. Remember, I want to make a transformation of x divided by b equals to x prime. Okay? So what is the phi prime of this x prime. If I'm looking now on average, I'm looking now on average field, okay? Or field x prime. The average field, okay, it is an integration of d dk divided by 2 pi over d phi, large phi, over k prime, e I k prime, k x prime. If I want to make a specific connection, this is what should I do? Okay, I know that phi of x prime equals to phi of b b x prime, it is x divided by b. Right? This is the big connection. Now, I plug it inside, so I know, oh, I'm sorry, I made a big mess. Let's start from the beginning. I want to define a new function. I call it phi prime of x prime, and it is an integration of d dk of phi prime of k e I k x prime. It's a function, call it a phi, let's call it phi prime. Okay? And this is the relation between the real space and k space of this new function. Now, I know the following. I know that if this is, oh, it's divided by 2 pi to the power d. So this is the Fourier transform. The phi prime over k, it is an integral of d dx of phi prime of x e minus I k x. So here I have x prime and x prime. Great. So I have this new function and the relation between the values of this function in real space and in k space. The next term that I'm going to do is to connect this small phi prime, to the large phi of my rescaled field. What we actually do is to declare the following. I'm saying that phi prime at x prime, it is the large phi of bx prime, right? I want to make this definition, okay? So what comes out of this definition? So phi prime over k prime, it is an integral of d dx, I'm using this guy, of large phi bx prime e to the minus I k x prime. And k prime over here, so k prime over there. Okay, now I'm saying, but b x prime equals to x. This is, you remember, I want to make a zoom out, and in this zoom out, the transformation was x divided by b equals to some new variable x prime. So this is why I'm doing this construction. So this is absolutely correct, but eventually I want to insert inside this integral the connection to the zooming out procedure. So what happens now? Now, I know that it is what? It is d. So if dx prime equals to x, so it's d dx b divided to the power d, phi, instead of bx prime, I have b of x, right? A to the power minus I k prime. Now, instead of x prime, I'm writing down x large divided by b. The next step is to recognize the following. It is an integral 1 over b of d dx phi of x multiplied by e to the power minus I k prime divided by b of x. Now this last integral this is why I started all this nasty business, because this is 1 over b of d phi over k prime over b. Right? So this is what I wanted to understand. What is this phi k prime over b? Because it's present in my effective Hamiltonian. This is why this additional step of zooming out is actually needed. Now let's see. So what I obtained eventually, that this phi of k prime divided by b, it is what? It is phi prime of k prime multiplied by b to the power d. Okay, b to the power d, and here I have equals to large phi of k prime divided by d. So I'm saying the following. I can take this averaged field, not at point k prime, but at point k prime divided by d. And it will relate to the averaged field by, after I perform the zooming out procedure, okay, multiplied by the prefactor of b to the power d. Okay. So what happens at this last step over here? This is where I'm located. I have H effective of, instead of saying it's some phi to the k prime, I'm saying it's phi small of k prime. Okay? And it is 1/2 an integral, this k prime smaller than lambda, k prime divided by b squared plus r b to the power minus 2 delta. Instead of phi k prime squared, I have average value of phi prime k prime b to the d divided by b to the d, and I have dk prime and squared over squared. We're almost done. So we have 1/2 an integration k prime smaller than lambda. What happens over here? We have k prime divided by b, k prime squared, b squared plus r. Here we have b to the power minus 2 delta plus d phi prime k prime squared dk prime. Remember, I don't know what delta is.
Okay.
It's 1/2 an integral. I plug all the b to whatever powers inside. So I have k prime average smaller than lambda. Here I have k prime squared multiplied by b minus 2 delta plus d plus r to the power minus 2 delta plus d and phi prime k prime.
Where did you get r to the minus 2 delta
It's
plus
b. It's b to the.
b plus r b to the minus 2 delta plus d. We're almost done because now the structure is very much similar to the original Hamiltonian. I remind you, the original Hamiltonian, h of phi of k, was 1/2 an integral k absolute value smaller than lambda k squared plus r phi k absolute value squared dk. This was the original Hamiltonian. This is the effective Hamiltonian. We worked really hard with a lot of rescaling, for the random variables. It's really, really easy. Here it's nasty. And the structure is very, very, very similar. This guy, exactly the same. This guy, exactly the same. These guys are exactly the same. Something happens over here. Okay. Now I want this to be almost similar to that. Okay. And I have a free parameter. The free parameter is this delta. I haven't decided what delta is. Right? Now, in the last 2-3 minutes, that's the time to choose delta. Okay? So I'm looking on this, I'm saying, if I'll take b minus 2 delta plus d, and I'll choose delta such that minus 2 delta plus d equals to 0. Okay, so delta equals d minus 2 divided by 2. Right? If I choose delta in such a way, okay, I'll obtain that my effective Hamiltonian of the average field, phi prime, averaged and rescaled, equals to 1/2 k prime smaller than delta k prime squared plus r multiplied by b to the what power? So 2 delta minus 2 delta plus d equals 2 b squared phi k prime squared dk. Okay. So the only transformation was very, very long, but eventually it's very, very easy. Okay, that I'm doing this average. I'm doing whatever. I'm going to k-space. I'm inventing this Wilsonian representation of a cutoff, etc., etc., etc. But eventually, the result is very, very simple. When you rescale everything and you zoom out, you'll get the same Hamiltonian. And the only thing that is modified is that r goes to r prime. So you have h, and which is an integral now in x space of grad phi plus r phi squared dx, and rg. The only thing that it does, you get again h equals to an integral of grad phi squared plus r prime phi squared ddx. The only difference between this Hamiltonian, where is this? Between the original Hamiltonian, it's only the RV squared. So the only thing that is affected by the RG step is that R goes to B squared multiplied by R. Okay. That's the only thing that matters. So the only thing that you do actually by averaging and increasing your scale, zooming out, the only thing that you do is that in the original Hamiltonian, this effective interaction R is multiplied by B squared. And that's it. That's absolutely it. So you started from this Hamiltonian, which is the Gaussian Hamiltonian. You performed a lot of averaging, coarse graining, etc., and you got the same Hamiltonian with slightly different parameter. So this means that this is the fixed point. And for like the central limit theorem, the Gaussian representation is a fixed point. The same happens over here. Okay. So if you start with the field theory, which is phi2, it's a Gaussian field theory, and you perform RG steps, RG coarse graining, the only thing that you're going to get is another phi to the second power field. Okay. Now, we already solved this previously. You don't need mean field to solve this, right? It's a bunch of Gaussian integrals, and it stays Gaussian. So we do have a fixed point. And we found it, which is the Gaussian fixed point. And the RG, the only thing that it does, it modifies R to B squared R. Now, this is us saying that if you start from a Gaussian, you sum up, you average, you end up with a Gaussian. You start with this Hamiltonian, you average, you end up with the same Hamiltonian with a rescaled parameter. And that's it. Now the question, and this is the interesting question, what happened if I'll start with a different field? Or with a different Ginzburg-Landau representation? If I had, instead of the Gaussian, if I had h of phi, an integral of gradient of phi squared plus r phi squared plus u divided by 4 phi to the fourth. What RG actually does, in a very complicated way, okay, it eventually modifies r prime, r to some r prime, and u to some u prime. And the question is whether this u prime converges to something very simple. For example, after several RG steps, u prime goes to 0, and then you're left with the Gaussian central limit theorem, or with the Gaussian fixed point, and then life is easy. Or maybe you have a different u prime that you converge to. Okay. So the question is, we found a single Gaussian fixed point, which is very simple. We know how to solve it. So this is the trivial example. It's extremely long, but this is actually the trivial example. Okay. What Wilson got his Nobel Prize for is starting with something like this, with a phi to the 4, and finding a novel fixed point, a different fixed point when the transformations not are leading to the situation when u prime goes to 0 and r prime is rescaled by b squared, but to some u star and b r. So to find this u star and some r star, this is the interesting part. So RG for random variables is very, very simple when you compare it to this stuff when you have a lot of integrals, etc., 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 etc. So we're done for today. Einat won't teach you today because we haven't done anything. We just have done a perspective. And hopefully next lecture we'll do the Wilson-Fisher fixed point. Okay, thank you all.
Last lecture is the next lecture is the last lecture.
It's the last lecture. Well, it's the last lecture. Yes.
שאלה, יותר קונספטואלית. היינו בפעמים הקודמות שהשתמשנו גם בנורמליזיישן, גם בקרוס טרנינג, שאנחנו מאבדים מידע.
כן.
עכשיו, על פניו,